we will take a look at this right now. So that is one of the key things to understand why this method is not the solution to everything, because this equation shown here tells you that you need a lot of time increments to get physically sound results. So we talked about your time step, your real time step, and this can be at maximum this value. So you take the minimum, and we've seen this, I've put this here on the right. So LE is the characteristic element length. Don't annoy me, stupid pen. So if you, for example, consider, just ignore this on the top. Oh, maybe we can incorporate this. And we see this is the mesh that we see in this body. Okay, and now the characteristic element length for each element is the smallest distance, the smallest direct distance between 2 points. So it would be this one for this element, it would be the one up here for this element, but for this element, it would be this height. And in order to have your entire method to be physically or yield physically sound result, it has to check for the smallest element in your body. Take that characteristic element length, the smallest of this very element, so this is indicated by the min here, and you have to calculate the dilatational wave speed, and then you basically divide the two, and what goes into the dilatational wave speed is the material density and the Lemaire's constant. So the Lemaire's constant are given through your elastic material properties. So you see, in this method, we only talk about elastic stress waves. That is a key thing to understand. You put an impulse on one node here at the bottom, and what the algorithm will do, because it calculates the accelerations, it will yield such a wave propagation through the body. And you see these also in so-called stress waves. So you could see if you look at the motions of the body, you see this wave propagating, but also stress waves. And the thing is that such an algorithm, if you think about, okay, whenever have you really seen a wave in a material, like in a solid material? You probably haven't, because the speed of sound is very high. In metal, it's, I don't know, between 3 and 5 kilometers per second. And that is actually the reason why you need so many time increment, because your CD down here is a very large number, especially for metals, and we're talking about metal forming here. So that's a huge problem with this algorithm, that if you deform metals, which have a very high CD, that you need very, very small delta T's. And usually this leads to a couple of millions of increments. Okay, so by what I've just told you, you can easily guess that this approach is quite impractical for quasi-static processes. That means, okay, quasi-static. Let's think about a tensile test. If a tensile test is performed at normal speed, you would argue that, except for whatever cracking occurs or the rupture of the entire specimen, this is a quasi-static process. So you'd say, yeah, if I need millions of increments, there is no need to simulate this using explicit dynamic analysis. Also, this is just logical, because there's nothing dynamic happening in a simple tensile test, right? So the advantage of this approach is for dynamic processes or for very fast processes, which usually like come along with dynamic aspects. But also, if you're interested in dynamic aspects of quasi-static processes, you should still go for explicit dynamic analysis and not classical static equilibrium-based FEM. Why? Because in static equilibrium-based FEM, you don't see any of these dynamic results. You have to put such effects artificially in this kind of FEM. In this FEM, the explicit dynamic one, you get all these effects for like just by using the method, because that's the way how it's constructed, right? So the thing is, I should be more precise. This method is impractical. Like, this word is giving me a hard time. Sorry, guys. If you simulate quasi-static processes in their natural time frame, so this indicates that we can maybe do something about it. I told you that with explicit dynamic analysis, we're talking about real time here, and if a real process takes 10 seconds, your simulation would run for days or even weeks. But maybe there is a way around this. And luckily there is. It's called mass scaling. Why does it work? So what is the goal of mass scaling? The goal is to reduce the number of increments necessary to fulfill the stability criterion. You remember, right? So this is the stability criterion over here that we have to fulfill to get physically sound results. And in order to still get physically sound results, but still fulfilling this criterion, we have basically 3 options. And the 3 options are listed here. It's called density scaling, which is classically called mass scaling because density times volume, blah, blah, and so on. But usually nowadays mass scaling encompasses these 3 things, of which the latter one, I've never seen anyone except me actually using this. Maybe I'm a weird dude, but I don't know if I invented this. I've never seen this before, but it actually works. So, but there's not so much right or wrong using the one or the other method. So let's just go through this. The density scaling or classical mass scaling, you would define a so-called scale factor of f square, let's say 16. Let's say your f square is 16. Then your stable time increment will increase by a factor of f. So that would be around 4. Why is this the case? I hope you remember. Let's go back. We see, we clean up a little bit. You see your density is down here. And you see this funny root here. So you can, and then the CD goes linearly into your stability criterion. And this explains now, if you do a density scale factor of power of 2, the actual gain in your stable time increment will be the square root of it. So don't get confused. You use 100, then your simulation won't be 100 times faster, but it should be very much around 10 times as fast as your original simulation, because your delta t is 10 times bigger. And if you have your total physical time that you want to simulate, for example 1 second, and you divide it by the 10 times larger delta t's, yeah, your simulation should be done 10 times as fast. Speed scaling is only recommended and a good choice if you have rate-independent materials. What does speed scaling mean? It means that if you have some sort of dynamic interaction, for example, you have a sheet and you have a die. And this die now touches, gets in contact, and eventually penetrates into the sheet. And if you now think about this punch moving at a very high speed, then you would consider this a dynamic interaction between these two objects. So if you don't have a rate-dependent material model, and if your speed of the punch is still sufficiently small, maybe up to 1% of the dilatational wave speed, this looks better, then the response of your sheet metal, should be independent of the speed that you assign to the punch. This feels unnatural because it's quite interesting to see. As an engineer, you have a natural feeling that most of the materials out there have a rate-dependent material response. And this is actually true. But if you neglect these rate-dependent responses and assume instead a rate-independent response, that's why I said it feels a little bit unnatural. But then the punch speed actually doesn't matter. So again, if you increase the velocity, holy cannoli, if you increase the velocity, your total t tot can be smaller, because the total time it needs for the punch to cover the same true distance, let's say d or something, is just smaller. So you don't have to divide a second by this amount of delta t, but just maybe 1/10 of a second by the same amount of delta t. So you don't change anything with your delta t, but rather your t tot, your total time that you need to simulate. But at some point, even if you assume rate-independent material model responses, you will see dynamic effects. So think about a sheet that you place between two pillars, and then you use a hammer and punch on it. You will see vibrations and all that kind of stuff. And these are not rate-dependent material responses, but rather wave propagation. These are dynamic structural responses. And if you increase the punch velocity too much, you will see exactly those kind of dynamic structural responses, which are only based on the elastic properties on the material. Even if the elastic response can be rate dependent, this is rarely used but could be. But even if the elastic responses are rate independent, and so are the plastic material responses, also assumed rate independent, even then you will see these dynamic structural effects like wobble. So if you see stuff like this happening, you have to reduce the punch speed, because this is then too much. Then you increase the speed too far. All right, size scaling. As I said, rarely used. I don't know. So the thing is, you could also alternatively, if you're afraid to alter the density and the speed, you could just make your problem bigger. So for example, you are supposed to produce a hood out of a 1 square meter sized sheet. Why not make this 1 square kilometer? For example, if you neglect gravity, it's usually just and you have a huge punch. Then what you do, you're altering this thing here. So ELLI, if we're going for explicit dynamic analysis, because we have to work in a consistent unit system, this is an actual length. This is now, before I said, yeah, you're talking in units, like time units, geometrical units, but now they have a physical meaning. It is millimeter or meter. So if you now make your problem, your model, 100 times as big, you increase your LE by 100 times. In this case, you would have to convert the forces, moments, and so on. So the distances and the forces cancel out, so your stresses, this is kind of cool. The cool thing about size scaling is your stresses remain constant. But if you do a force or moment-based analysis, of course, if you form a 1 square kilometer wide sheet, you can imagine that your 800-meter punch in diameter requires a lot of force. But if you know how much your size scaling was, you can just divide your final results by this. So I find this a neat approach, but maybe stick to the first two so that your supervisor will not be confused because you used size scaling. Okay, so much for the mass scaling. So we can actually do something about that. This method is technically very impractical. Yeah, this time I did it right. For quasi-static processes, which is basically the case for most metal forming processes.